Here we go, topic 3. Welcome. We're going to look at the attack of the sun today, but we never really finished up with our down to the Earth's core here. Also, you might remember that we had a cross-section of the Earth quiz, and you can see here that we got 2 attempts, and it's going to close the 29th. And that's flexible also, that the closure date on that. So it's not always that, you know, if there's been some kind of issues, please let me know what special cases you might have, and then we'll see what adjustments we can make. But I think that's plenty of time to get that done. And then you've had the basic development of basic units up in here. So those are the 2 major assignments that have been, that you should be kind of getting a handle on at this point. Then also the textbook, Smart Geothermal, Guide to Smart Geothermal, right here. There are some assignments in here, and this first assignment's not graded, but the questions will be, some of the questions in the quizzes will be from the actual introduction. There'll be the 5 questions in this material, and that's was in this quiz that I think you're going to see that here this week. Down here, got the tectonic plates in the Smart Geothermal here. So this quiz is going to be on the plate tectonics and Smart Geothermal, reading in your text. And this is the basis of geothermal energy exploration. You have 1 attempt, 1 hour, complete the quiz. Be sure to read the chapters 1 to 3 in your text. And some coaching for you on the taking these tests online. You know, it's good that you have a solid connection, a relatively fast connection, and then save every question, you know, that you take when you're taking the quiz. And these questions will be paginated such that 1 page, 1 question, and that way you save each question. And if something happens where you crash out or something, your computer goes down, you don't have to try to start from the beginning again and lose everything. So save every question, and then do the assignments before you start the test, so that you can satisfy the time requirement. And once again, if there's any special issues that you have, please let me know. And you've got my email address, so it's a way to contact me, or through the forums also. So Joe came in for the lecture today, and we wanted to look and see, kind of maybe update you. The 2014 practicum is in your course shell there, but here we went into Missoula Energy Tech in YouTube, and here's the Missoula College Energy Practicum. This is kind of an overall view.
When we got down here to the practicum, we were instructed to build a solar voltaic trainer system that could be used virtually with anybody, whether it be the youth or adults. So what we've done, we was given instructions to construct a solar voltaic trainer. We started out with an initial plan. We had to draw our schematics to get it down on paper so we could start building. We started with our frame first. Most of the frame is made out of wood. We had to start with the bottom and come up to the top. We left our panel off here to...
You know, you come to lecture, then we're going to feature you here, right? So here he is. This is the presentation. That's when we went to the winter. Yeah.
Well, good morning, people. Thank you for showing up here, community members and students in other projects that were developed here. It's been a great honor to work with his team members and stuff. We have 2 high school students and 2 possible engineers here. I'm just a dinosaur, probably on the last stage of everything, so it was really educational. We created a system that hasn't been created yet, so hopefully you guys could be able to benefit with some of the results and stuff that we got off of these things. So with that, I'd like to, Trinidad. This is Joe, and this is Cora, and Forded Lance, Aaron Lance. And it was really impressive to have the high school kids with such knowledge. I mean, when I was in high school, I think we still doing the dinosaur stuff, and with their technology and abilities with computers was totally amazing, and the thought process, and we kind of learned a little bit from them, and I'm sure they learned a lot from us. So with that, I'll have Trinidad take over some of the...
All right, so slide, intros. So I'll start with what we did. We built and tested 3 different solar thermal designs, just to kind of have like a variety where we could assess the differences in materials to come to different conclusions based upon the data we collected during the several weeks. We have 3 designs here. This is the flat panel water heater, and it's 8x4 piece of 1/2 inch plywood with 1x4 sidings along the side there. This left side is copper piping. It's 50 feet of copper piping, 1/2 inch diameter center, and basically you can't see it on the, from the side, but behind this there's 2 5-gallon buckets full of water. Intake from here, circling inwards, and as it's circling inwards at a velocity of, doesn't really matter, but anyway, it was just pumped in there through a submersible pump, 8.4 watt pump, and it'd go into the center, and as it's circulating, it's being warmed by the sun's radiation. This is 50-foot copper, and this is 100 foot of irrigation piping. This one is the concave, like octagonal design, where we put 8 wedges, two pieces of wedges, I think, like a, what is the angle on those? 30 degree angle on the wedges, and still 50 foot, feet of copper, 1/2 inch diameter, and same system, intake and then outlet into the same 5-gallon bucket. So the area of the collector on all 3 is 32 inches by 32 inches. That's 1,024 square inches. So it's absorbing a good deal of energy. So good surface area. Why we did it? Just to learn new things. We all have an interest in renewable energy, and we all consider it to be the future. It is effectively heating water that's being circulated through the efficiency of the collector. It's just power out over power in, which is heat flux times area of collector, and then the solar constant, which is about, it fluctuates, but it's about 1,000 watts per square meter, and so that's what we use, 1,000 watts. The total energy that was accumulated over a 6-hour period within the water was about 2.76 megajoules, which is a good deal of energy. Total power was about 0.766 kilowatt hours, and then the efficiency of the copper tubing, 50 foot of the copper tubing, was about 17%. Copper is a good thermal conductor, and then the irrigation, which is like a plastic tubing, but good efficiency, 26%. And wood, some piping, some sand, that sort of thing. It was nothing too expensive. The savings we made was about, let's see, kilowatt hours for 8 hours a day on the pump. That's only electrical charge we have for the entire project would be about, you know, look at this, it's like really small, and then an annual price would be $250 a year, you know, so that's like nothing. And then I compared it to a Home Depot electrical water heater using 12 kilowatts per day, and you know, we came up with an annual of $430 a year. So the difference was $435. Oops. And then the total annual savings was, you know, $150. So it's like 50% of the total cost of the solar thermal water heater. So, you know, it's definitely something that if you have the money, you should. Now we're off to method.
All right, here comes Joe.
The savings was, you know, $150. So it's like 50% of the total cost of the solar thermal water heater. So, you know, it's definitely something that if you have the money, you should. Now we're off to methods and results, and Joe's going to go.
Thanks, Ernie. So our original idea was to build one flat system that had the copper tubing and the plastic tubing to get a kind of a comparison between the two different materials. And so the plastic tubing, we wound that up. That's a 100-foot section right there. And we got to the copper, and that was a little problematic. We couldn't, I don't know if you've ever tried to bend copper tubing by hand. You can destroy it pretty easily. So we couldn't get it tightly wound like we did with plastic. So we went with just a 50-foot section that we could get about the same area covered with some spacing in between the coils. And just to kind of think outside the box, we decided to build this other little system that has kind of a concave shape, and it was you know, it was not easy to build, but I think it turned out pretty well. So these are the two products side by side, or the three systems really. The concave one sits by itself, and the other two sit on one sheet, so we can cover them all at the same time. Let's see. So then we decided to put sand in it for some thermal mass to see what that would do. We definitely saw a little bit of a rise in all three systems with the sand in it. So that sand would heat up, and we had a lot of clouds coming through, and every time the clouds would come by, the solar insulation would drop dramatically, but the sand would continue to radiate heat to the tubing. There's a good shot of our end product. We have our solar insulation meter measuring the insulation. Every time we take a measurement of the water, we get the solar insulation as well. We got to play with the thermal imaging camera. Thought I'd throw that in there. It's kind of cool. So you can see, you know, this crosshairs shows the degrees, 122 degrees on that collector. It's pretty warm. So here's some data. So we got this is the copper line, the blue line. The yellow is the plastic. And this gray line is the secondary axis, and that's the solar insolation throughout the day. So you can kind of see how it was kind of all over the map. This one that you got, the gray line is well, the gray line is the ambient air outside, and then the blue line is the water in the collector. And this is the concave one with the sand. You really see this red line is the solar insolation throughout that day, and it's just all over the place. But still, steady incline.
It is.
And now I'm going to hand it over to Lance.
Okay, so as a sub-project, built a one-way valve and 3D printed it. So here it is, and it's goes in between. It goes right off the pump. It's going into the collector so that it doesn't have backflow. So it just pushes the door out of the way, and then when water tries to come back, it closes it. Yeah, 3D printed that, you'll see that later. You would like to?
It'll be out there in
Oh,
our
yeah.
presentation later.
Alright, so I'm gonna introduce it.
Thank you, Lynn. We just, on behalf of our team, we just want to thank Dr. Barlayton, Tim Chester, Jonathan Bow, Wally Higgins, and any other faculty for putting together this practicum and helping and giving input to our projects and for giving us this experience. And thank you guys for coming. And now we're just going to open for questions.
You've mentioned thermal insulation several times. What does that mean?
So the thermal insulation is, that is the amount of solar radiation hitting the earth at any given point. It's usually measured in watts per square meter. Just kind of an average of 1,000 watts per square meter they use for like calculations and stuff. But if, you know, a little bit of clouds will drop it down from 1,000 to 250, you know. That's a significant drop.
Solar thermal. Very big shape.
There's a ladder.
Okay.
So how's your 3D, your NCAD? All right, man. Let me know when you get that thing fired up, will you?
Oh, yeah.
Thanks.
So I'm gonna go over some of these power equations with Austin. You want to babysit on that for a little bit? And that's, so I think this is something that,
3.2.
well, it's something that I teach kind of over and over. I think it takes a while, so grab some notebooks, yeah.
Okay. So now, that's the bottom. Like this. See? Okay. Now, the first part is this.
It's just, it's like, with chalk dust, like, okay, the chalk dust is going to, like, that stuff has to go somewhere. It's still like, this is good. The eraser is full.
Hollow.
You get it to learn it?
Yeah, do a little, with
And you have to
the
be
system.
in 3 for you.
Three.
1, 2. 7, because it's not 2. It has to be.
Yeah, so what
8,
you're
7.
going to be doing, you take that
So it's
mechanical energy.
0.279.
Maybe this
So this needs to be
eraser's kinda small,
110
this is
because it's on the
one,
wrong side.
10 units of energy inside here.
There we go.
If
That
the sine
That's about 2x there. Hey, there it is. You did good, Joe. So we took a quick look at the practicum that Joe participated in. That was his presentation on the solar thermal. And I mean, that's good. That you can also use the geothermal though to cool your house. And seeing as how when you get down in the tropics, you know, it's more of a cooling issue than heating. So maybe later today we'll take a look at our Google Earth download here, which is what I'd like you to do. So you have this available to you on your computer. Let's see where we go. This is the assignment here. You know, Google Earth had just a major, so we say, update, and what we might have to do here is actually get into YouTube or just actually search for Google Earth. I'll do that on my own here later on. But that link now, it looks like it's no longer active. So, but let's take a look back here at the down to the core. As we were looking at that last week, down to the Earth's core. In place of this Missoula Energy Practicum 2014, the methane generation, which we did look at, Hull's Dairy. You can take a look at that on your own. But let's get back into the down to the Earth's core. So we left off about
an asteroid bigger than an entire city.
Right here. Take a look at the layer that was laid down, theoretically. Proof being in the strata that's there.
The compressed remains of a long-forgotten desert. As wind and water move material around the planet, new layers built up above. One layer buried another and another, squeezing the material beneath until they turned to rock. Basalt, once a mighty volcano ground down by wind and rain.
As they start digging, this is their digger right here. You can see the depth meter. 536 meters, 547, 550.
This layer isn't like the others. It's thinner and seems to go on forever. It contains an element called iridium. Iridium is rare on Earth, but abundant in space. Nearly 600 meters inside the Earth's crust, a layer of space rock. 550 meters beneath Denver, Colorado, we've discovered a layer of extraterrestrial rock. Once this rock sat on the surface, which means Denver was covered in space dust. It sounds like science fiction, but the reality is even stranger. An asteroid bigger than an entire city. $65 million years ago, it plunged straight towards Earth, to a planet.
See, there's Uncle Dino. This is kind of where we left off last week. Right here, that's my great Uncle Dino right there.
Ruled by dinosaurs, where T-Rex reigned unchallenged. He was as heavy as an elephant. His meter-long jaw was engineered for maximum bone-crushing action.
All right, let's go down a little deeper here. Because you know what happened to Uncle Dino? He turned into petroleum, huh?
Oh. There was a shallow sea here.
More basaltic.
mobile phones are all made of quartz.
Amethyst. So we're starting to talk about heavy
Iron
pressures.
impurities made this quartz
Heat.
purple.
In essence, the geothermal then.
It's an amethyst.
It's amethyst. At roughly 10,000 feet, anywhere in the earth, anywhere 10,000 feet below the surface of the earth, you're going to find temperatures around 300 degrees centigrade. So, 3 times what you need to make geothermal, large-scale, enhanced geothermal plants operate. But you do have to transport that 10,000 feet up. That steam and things are going to cool off. So that's when we're going to talk about piping and techniques, drilling techniques. But then it's not all going for 10,000 feet. You can do a lot of good at 8 feet, 6 feet below the surface, which is the essence of our experiment in medium temperature.
Sapphires, rubies, emeralds, it takes millions of years of wind, rain, and tectonic plate movements to bring them near the surface. But for every gem we find, there must be tons buried, never to be seen.
Not our lifetime. There you go. 2,900.
We're nearly 4 kilometers down. Mankind has looked into distant space, visited the deepest ocean. But no human has ventured beyond this point. It's time to enter the unknown. We're deeper than any human has ever traveled. 4 kilometers inside the Earth's crust, beneath the floor of the Gulf of Mexico. Around us, a layer of rock hundreds of kilometers wide, over 1.5 kilometers thick. It's salt. Trillions of tons of salt. We use it to grit our roads, flavor our food. In fact, without salt, we'd die. But how did trillions of tons of salt wind up here, beneath the ocean? $160 million years ago, a vast scorched basin stretched between Texas and the Yucatan. Like Death Valley, it was below sea level and hot.
Here's where we start to see the essence of tectonic circulation, or the crust circulating down into the mantle, and the convective gradients, or the heat from the core. Remember, the core of the Earth is the fuel, and the mantle of the Earth, the area around the core, the molten plastic, is the engine.
Briny springs bubbled up through the bottom of the basin. In the intense heat, the water evaporated quickly to leave a thin salt crust. Over 2 million years, the salt grew thicker, until we're back where we started, inside a layer of salt that's over 1.5 kilometers thick, buried 4 kilometers beneath the floor of the Gulf of Mexico. Sealed below the salt, 5.5 kilometers down, a layer of porous sandstone full of a thick, black liquid. We've struck oil. More than coal, gemstones, even gold. This is the underworld's greatest gift to us. Oil dominates our lives more than any other geological substance. And every time we turn the ignition, we do so thanks to a chain of events that stretch back 155 million years.
So this is kind of dated material. I don't know if you noticed at the beginning of the course, one of my statements, and one of the things that I think is current science in the future is that we don't really need to burn stuff anymore. That the Earth, the geothermal aspect of the Earth, the convective gradient, the cycles in the mantle, and the geomagnetics that are generated by that cycle will create all kinds of different energy that we're using, you know, dark energy, plasma forms that we don't really need to burn stuff anymore. So oil is indeed a gift, but let's think about the retrofitting that we're going to look at as far as the fracted out reservoirs, where we're going to talk about fracking is where you break the structures underground and form these cavities or areas that you can store salt water or other fluids in, and that's where the oil comes from, those cavities. They break them open the rock up, suck the oil out, and leave these fracted out reservoirs. And we can repurpose those for geothermal harvest on a large scale. And there's more than we're going to need at this point of exhausted oil wells, so we really don't even have to drill the hole anymore.
5 million years after the salt pan formed, there was a prehistoric sea here, home to trillions upon trillions of microscopic plants and bacteria.
So that's how our oil was formed. Let's go on down a little deeper here. What's important is that you understand that the fracted out reservoirs from oil and gas development
6.4 kilometers inside the Earth's crust, beneath the Pacific Ocean. Heat from deep inside the Earth drives magma up, forcing it through the crust and into the ocean.
Here you see the essence of the replenishment of the suboceanic plate, and we're going to see how that works in our tectonics here, but the volcanism associated with that transport.
As the molten rock cools, it builds an immense underwater mountain range. This is the very youngest land on the planet.
And there's two big things you got to have. You got to have some type of coolant or some fluid to circulate into the systems to transfer heat, and you got to have heat. And so what we're finding for current experiments in geothermal harvest is actually tapping into these suboceanic volcanoes. There's plenty of water, and there's your heat, and then you just got to get it up to the surface, or actually install turbines and stuff, and then transmit the power.
The birth of new crust. Older makes way for new. But the Earth isn't getting any bigger. So what happens to the old crust? There's only one way to find out. Follow it. Moving west at about 10 centimeters a year. At this speed, it'll take 170 million years to follow the crust across the Pacific. Time to hit fast forward. We're riding the Pacific Ocean plate away from America towards Asia. The crust is sliding down into some kind of chasm. This has to be the legendary Mariana Trench, the deepest point on the Earth's surface. We're at the trench's rim, 5 kilometers beneath the ocean's surface, far below the reach of the sun's rays. An anglerfish. Like a firefly, it's generating its own light, switching it on and off to lure in its prey. Six and a half kilometers down, deeper into the abyss. Eight kilometers down, we finally reach the ocean floor. But one section of the trench descends even further. "11 kilometers below sea level, this is the lowest point on the planet's surface. The Challenger Deep. Deeper than Everest is tall. Pressure is over 1,000 times greater than at sea level. It would squeeze every last square centimeter of air from our bodies until we were compacted like a crushed car. The trench is where the Pacific Plate meets another of the great plates that make up the Earth's crust, the Philippine Plate. The Pacific Plate is saturated with water. Its rock compacted over millions of years beneath the weight of the ocean. It's so dense, at high speed we can see it plunging beneath the lighter Philippine Plate. This is where the old crust goes. Here, 11 kilometers under the Pacific Ocean, the Earth swallows the old crust. Our planet is literally eating itself. We're back inside. Make the surrounding rock transparent, and we can see there's molten rock all around us, rising up towards the surface. Molten rock is less dense than solid rock, so like heat, it rises.
So you've all seen your lava lamp. This is the world version of the lava lamp. You can actually see it's probably that's what they used right there with some molten wax. But when we looked at the cross section of the Earth in last week's lecture, I think we saw the plumes, and these are the plumes of magma right here. Remember, it's lava when it comes out of the surface. It's magma when it comes out. Definitely a lava lamp, yeah.
And keeps rising. This is as close as it gets to hell on Earth. We're inside a vast chamber full of billions of liters of molten hot rock. The pressure is overwhelming. It forces gases and water out of the magma up at high speed, until they punch through the crust to erupt as a volcano. A terrible, beautiful monument to the immense power locked within.
Let's take a look at that right quick here. Let's see what's really going on Earth at this very moment.
Hello, welcome to Newsline. I'm Miki Yamamoto in Tokyo with the latest news at this hour. A volcano on Japan's southwestern island of Kyushu has erupted. Mount Aso has been sending plumes of smoke and ash into the air. An NHK camera has captured images of black smoke rising high above the crater. The meteorological agency says the eruption occurred on Monday at around 9:43 a.m. local time. That's about 2 hours and 15 minutes ago. Agency officials observed smoke rising as high as 2,000 meters. They saw large rocks flying near the site of the eruption. Officials have raised the alert level for the area to 3 on a scale of 5. Level 3 means do not approach the volcano. The agency is calling for caution against falling volcanic rocks and pyroclastic flows in areas within about 2 kilometers of the crater. Aso city officials say some 20 to 30 people, including tourists, were near the crater at the time of the eruption. They say all of them have evacuated to safety. The government has set up a task force in the Prime Minister's office. An official with the meteorological agency has shed more light on what happened.
We found that the smoke rose not only vertically, but also horizontally. The eruption could have pyroclastic flows.
Disaster Management Minister Eriko Yamatani has called on bureaucrats across relevant ministries to work closely with officials in Kumamoto Prefecture to gather information and ensure the safety of the residents.
There you have it, in the Ring of Fire, which we're going to study here very soon.